In this video, we will continue our discussion of synthesis involving nucleophilic additions to polar pi bonds as key bond-forming steps. In particular, we will move our focus to identifying synthetic traps and learning about the protecting group schemes that allow us to avoid problems such as functional group incompatibility. In the previous video, we learned about the synthesis of organometallic reagents, oxidation reactions, and hydrogenation reactions, and practice using those in synthesis questions. We will move on now to the protection of alcohols, functional group compatibility, and utilizing selective reactions. Step 1 still applies. Do not panic. We will begin part 2. Similarly to part 1, I will have you pause and try to propose a synthesis for the conversion of the given starting material to the desired product. Now, keep in mind you might not be able to fill in all the blanks, but what I would definitely like for you to do is to work backwards, try your retrosynthetic analysis to at least provide the structures of the necessary intermediates for this synthesis. Like last time, if you like, set a timer for 5 minutes and give it a shot. Functional groups in the product are an alcohol and an alkene. We see there's also an alcohol in the starting material, so I bet we don't have to make that, but we will have to generate the alkene. So now in my head, I am thinking about all the ways I know how to make alkenes. Or if those methods are not in my head, then I'm using my reaction charts. Then I map on the carbons in the starting material, since I'm pretty sure that this alcohol is that alcohol. Maybe not definitely, but that's where I'm going to start in my analysis. And then I note that this bond must be made, the double bond of the alkene. Super, there's an aldehyde in the starting material. I suspect that this transformation was accomplished via a Wittig reaction between an aldehyde functionality and a Wittig reagent, where the two carbons of the alkene made the bond via Wittig reaction mechanism. The fake mechanism, of course, is just you're putting together the carbonyl carbon with the ylid carbon and they make a double bond. So this looks right. This seems a bit too simple. Is it really just mix those two things together? Let's look at the other functional group, the alcohol. What do we know about alcohols? We know a lot. We know a lot about their reactivity. In this case, I just want to point out the pKa of the alcohol proton. It's 16. And the Wittig reagent, it is a nucleophile. It's electron rich. It has carbanion character. It is a carbanion. It's a stabilized carbanion, but it is still a carbanion. So the Wittig reagent is basic, and the alcohol is mildly acidic. It can be deprotonated. What will actually happen when we mix these two species together is not a Wittig reaction. It's simply a proton transfer. I've redrawn these two species on the left side of the screen. Let's investigate that proton transfer quickly there. Here are the specific alcohol and phosphonium ylid involved in this proton transfer reaction. I've also written out a generic example below. We'll draw the arrow pushing on the generic example. The basic ylid can deprotonate the alcohol to generate conjugate base of the alcohol, which is an alkoxide, plus this species. And together we have a salt. In the specific example, the electrons, basic electrons from the phosphonium ylid would deprotonate the alcohol, generating an alkoxide and the protonated Wittig reagent. An undesired proton transfer reaction would occur rather than the Wittig reaction. This undesired reactivity is our first example of functional group incompatibility. And really, we have seen this before. Want to avoid proton sources, such as water or alcohols, in the presence of carbanions, such as Grignard reagents, organolithium reagents, dialkyl cuprates. These are all sources of carbanionic carbon, and also Wittig reagents. And while we're making this list of nucleophilic reagents, electron-rich reagents that we should avoid exposure to water, we also discuss lithium aluminum hydride, which is a source of hydride, must be kept away from water as well because it is basic. So it is also incompatible with alcohols. What does it mean for this synthesis that this key step that we've identified, this key transformation, this Wittig reaction to make the alkene, will not work with both the alcohol and the aldehyde in the same molecule? Can we do anything, or are we just stuck? Yeah, we have to protect or mask one of the functional groups that is incompatible. And we want the ylide to react with the aldehyde, right? That's the whole idea here. The functional group that we do not want to react is the alcohol. So our solution will be to mask or to protect the alcohol. The term that you'll most commonly encounter to describe what we're about to do is protect, but really it just means mask or hide the alcohol during the reaction with which it is incompatible. Before we learn how to hide, mask, protect the alcohol, let's take a look at one more example where this might be necessary. We now know that when a molecule has multiple functional groups, one must consider the reactivity of all of those functional groups when proposing a synthetic step. For example, the transformation proposed below does not give the product shown. Why not? To be sure that you can apply what you just learned, pause the video and propose an explanation for this observation. If you like, set a timer for 5 minutes. Before we can explain why the proposed transformation does not occur, let's consider why the chemists thought it might occur in the first place. There is an epoxide and a nucleophile. In this case, that nucleophile is a Grignard reagent. It's really nucleophilic, so this is basic conditions. We know that for epoxide openings, we must first think about whether or not the reaction occurs under basic or acidic conditions. And certainly, these represent basic conditions. The chemist thought that the less sterically hindered, the less substituted carbon of the epoxide would be opened by the nucleophilic Grignard reagent, making this carbon-carbon bond. Consistent with this analysis, the chemist proposed that in an SN2 step, the electron-rich Grignard reagent attached sigma star CO of the epoxide at the less substituted carbon, carbon number 1, again generating this key bond. After workup, the alkoxide will be protonated, generating the alcohol. So what happened? Yes, we neglected to consider a functional group. What about the alcohol? What about the alcohol, you might say? Well, Grignard reagents are really basic. But what happens when an alcohol or water is exposed to a Grignard reagent? Let's write it at the top of the screen. Grignard reagent is basically a source of carbanions. It's very anionic carbon. So this is, as we said, it is basic. The alcohol can act as an acid. It has a pKa of 16. If the Grignard reagent deprotonates the alcohol, acting as a base, this would generate an alkoxide and an alkane. Thinking about the reverse reaction, going from the alkane acting as an acid, it's the conjugate acid of the Grignard, and the alkoxide acting as a base, the alkane would have a pKa of around 45. So to calculate the equilibrium constant for this reaction, since it's a proton transfer reaction, the equilibrium constant is 10 to the difference of the product acid's pKa minus the reactant acid's pKa. So 45 minus 16, which is about 10 to the 30th, which is much, much, much greater than 1. So when Grignard reagents are exposed to alcohols or water, they make alkanes. Boring. All we can do with an alkane is burn it. We don't want to burn it right now. We want to make carbon-carbon bonds. We don't want to make carbon-hydrogen bonds. So we must avoid this functional group incompatibility of carbanions, such as Grignard reagents, or phosphonamylides, and alcohols, or water, or carboxylic acids. Acidic protons must be kept away from carbanions. So what really happens when this epoxide is mixed with a Grignard reagent? Well, exactly what we diagrammed up top. And try yourself first if you want, but it's going to generate an alkoxide and an alkane. And of course, there's still magnesium salts around. All right, now that we know the problem, alcohols must be kept away from carbanions, let's figure out how to solve that problem. Let's learn how to protect alcohols. The most irritating part of protecting alcohols is all the acronyms. Let me just summarize for you how we will protect alcohols, and then we will get into the acronyms. So the issue with the alcohol is the acidic proton, right? That was the issue. It kept being deprotonated by these carbanion species. So we need to replace that hydrogen atom with something that is not going to react with the carbanions. So the way that we do that is by replacing the hydrogen with silicon. Okay, so we're going to make the silyl ether. To make the silyl ether, we'll need to treat the alcohol with something that contains silicon. Okay, so we're going to use this type of species. And what will essentially happen is that the oxygen of the alcohol will make a bond to silicon in an SN2. And then there'll also need to be a base because something will need to soak up this proton. All right, so it'll be an SN2 proton transfer, and then we'll have the silyl ether. So now instead of the proton, there's silicon. So you're not going to have this issue of oxygen having this mildly acidic proton anymore. So you're going to do stuff to the silyl ether, blah, blah, blah. So let's just write do stuff. But all that stuff that you're doing is going to be happening in the R group, right? The alcohol part will not react. That's the entire point. Okay, we did stuff. Great. Now this R group is different. Now ready to remove the silyl ether part because it was only there to hide the acidic proton during the stuff. So we need to remove it. How do we remove it? Well, we're going to remove it typically with fluoride. Fluoride and silicon make really strong bonds. So you'll have fluoride and then you'll have some sort of proton source. Let's just put water. Fluoride is going to bond with silicon. It'll do an SN2, displace silicon from oxygen. And then, of course, the proton source that just will reprotonate the alcohol. But it's not the same alcohol because we did stuff to the R group without affecting the alcohol, right? So we started out with the alcohol, we get back an alcohol, but the R group has changed in some way. So overall, we will protect, do stuff, and then once we're done doing stuff, we're going to deprotect. We don't have to hide the alcohol anymore. Now that we have the general idea, that was pretty fun, let's get into the specifics. So alcohols can be protected as silyl ethers using either trimethylsilyl chloride or terbutyl dimethylsilyl chloride. Quite frankly, there's a gazillion different silyl ethers that alcohols can be protected as. I have shown here the two of the more common ones, and you'll see them in your textbook if you choose to read it. So trimethylsilyl chloride, that's TMS chloride. And then again, pyridine is used to soak up the acidic proton. We can briefly draw out the mechanism for this protection. So again, there's a substitution reaction. Oxygen and silicon make pretty strong bonds. Think about sand. Everyone's seen sand before, right? Yeah, sand's pretty stable. And sand is just silicon dioxide. So silicon and oxygen make pretty strong bonds. So now we have this species. This is pretty acidic, this proton now. And that's where pyridine comes into play. Pyridine, it will soak up that acidic proton because it is a base. An SN2 followed by a proton transfer gives us the silyl ether. Or if you use TBDMS chloride, which is just, again, just a bigger silyl ether, contains a T-butyl group. Ooh, fun, chicken foot. Dimethyl chloride, there we go. And then pyridine, you would get the TBDMS ether. Doesn't matter, pick an acronym and stick with it. So we have the protection, and once you have this silyl ether, you do stuff to it, to the R group. And then once you're done doing stuff, you're going to deprotect. Deprotection, again, as we said at the beginning, utilizes fluoride. Fluoride makes an even stronger bond to silicon than oxygen does. So we'll draw out the TBDMS ether. This works with TMS as well. THF that's the solvent. We've talked about THF as a solvent. And then TBAF is tetrabutyl ammonium fluoride. It's a salt, a specific salt of fluoride, tetrabutyl ammonium fluoride. Tetrabutyl ammonium looks kind of scary. It's just there to make the fluoride soluble in an organic solvent such as THF. Fluoride would do an SN2 on silicon, making a nice strong silicon fluorine bond and liberating the alkoxide. To form the final alcohol product, the alkoxide does need to be protonated. The solvent system for these reactions often contains water, and water can serve as the proton source. A final proton transfer unmasks the alcohol again. All right, we know how to protect alcohols. Time to use what we know. So we have our two syntheses that we could not get to work as desired before. You can now propose a synthesis that will work for both of these problems. So there's this problem, and there is this problem that we started out with, introducing functional group incompatibilities involving alcohols. So take a few minutes, pause. Maybe you want to give yourself 10 minutes this time, 5 minutes for this problem, and 5 minutes for this problem. All right, ready, set, go. For this problem, we map carbons 1, 2, and 3 to these carbons in the product. We know that this is the key carbon-carbon bond formed from reactant to product. We know that epoxides are electron poor. There's a partial positive on both oxygens of the epoxide. But we can see that carbon 1 is the carbon that's attacked. That is the less substituted carbon of the epoxide. So that tells me that this reaction would have been conducted under basic conditions. Of course, since the atom making a bond to the epoxide carbon is another carbon, then our only option really is basic conditions. Since carbon 1 is electron poor, it's an electrophile. What I'll call carbon A must have been electron rich, a nucleophile. This nucleophilic carbon most likely came from a Grignard reagent. Now, not only is there an epoxide in the starting material, there's also an alcohol. We have learned that alcohols and Grignard reagents are incompatible, so we know we're going to protect the alcohol first. We will do so as the silyl ether. We will use either TMS chloride or TBDPS chloride. A reminder that TMS chloride is trimethyl silyl chloride. Protection generates this intermediate. You can either draw out the silyl ether, or you could just use the acronym. TMS stands for this trimethyl silyl. From the protected alcohol, we can treat with the Grignard reagent to effect the desired ring opening of the epoxide. A workup step is needed to protonate the alcohol, taking a look at the product. So in our generic scheme of why we would protect alcohols, this part, adding the Grignard reagent to the epoxide, is an example of doing stuff. While the alcohol is protected, we modify the R group. We did stuff to it. Okay, now that we've done stuff, it's time to deprotect, and then we will get the final product. So to deprotect, we'll use TBAF, that's a source of fluoride. And we'll use THF and water. THF dissolves everything organic, and water is how we will obtain the proton on the alcohol that we're unmasking, so this alcohol. Cool, we did it. This synthesis demonstrates how protection of alcohols can be used to avoid issues of functional group compatibility, such as between electron-rich basic Grignard reagents and the mildly acidic proton of the alcohol. Still, retrosynthesis was key in figuring out the overall synthetic scheme. Wonderful. Pause, revise if necessary, then let's take a look at the very first problem that we discussed when thinking about the utility of protecting an alcohol. For this synthesis, we identify the Wittig reaction as the key step in forming this alkene functional group found in the product. However, as we discussed, alcohols, such as the one contained in this aldehyde, in this molecule with multiple functional groups, alcohols are incompatible with carbanions such as phosphonium ylides. They will simply undergo proton transfer reactions. So to avoid this, during the key Wittig transformation, we will first protect the alcohol. This time, let's do so with TBDMS chloride, which is just another silyl chloride that can be used to protect alcohols. You can use TMS or you can use TBDMS. For your purposes, they're interchangeable. For the purposes of a synthetic chemist in lab, they are slightly different, but that's not your problem on paper. Excellent, we've protected that alcohol. Now time for the doing stuff, right? Now time for that key Wittig step. So just as planned, we're going to use the phosphonium ylide that delivers the 5-membered ring found in the product. Now that the acidic alcohol is masked, the Wittig reaction will be successful. To generate the final product, all we need to do is deprotect. We will use again TBAF, a fluoride source. Fluoride will make that strong bond to silicon, remove it from oxygen. And we'll use THF with some water. Protonate the alkoxide. All right, not so bad. Now that we know how to protect alcohols and use those protection schemes in synthesis, let us move on. We will move on now to how to protect aldehydes and ketones. Everyone can take a big sigh of relief because we already know how to protect aldehydes and ketones. These are reactions we've already learned. We're just going to practice using them in synthesis problems. Aldehydes and ketones, such as benzaldehyde, can be protected as acetals. For example, the dimethyl acetal. You could use some strong acid catalysts, such as tosic acid and methanol, because that delivers the alcohols that will generate that acetal. The choice of methanol and the dimethyl acetal was arbitrary. We could choose any alcohol if we wanted. We could treat with ethanol and a strong acid catalyst and generate the diethyl acetal. Oh, we could get fancy and treat with the diol, a diol, such as this one, and a strong acid catalyst and generate a cyclic acetal. It really doesn't matter. You can let your imagination run wild or choose one type of acetal and stick to it. Either way, the aldehyde functionality is protected as the acetal. So remember what we said, acetals are stable in base. So acetals are stable under basic conditions. So now imagine we want to modify the R group. We could do that. This is the doing stuff. So do some stuff under basic conditions or neutral conditions. The acetal will be stable. Of course, we don't know very many things right now today that we could do to that phenyl ring, but just pretend we will soon know. But in the meantime, you can just pretend it's an R group. We've done stuff. Yeah, all right, it's different. And then once you've done stuff, then deprotect. How do you deprotect? How do you remove an acetal? Yeah, you already know how to do that. Acetals can be deprotected to reveal the aldehyde or ketone again once you've done stuff to it under acidic conditions. This is simply acetal hydrolysis. So using, again, a catalytic acid, but this time with water around to generate, reveal the aldehyde or ketone again. So this oxygen from water, that oxygen, and of course, 2 equivalents of the alcohol of methanol generated from here. So let's practice using this protection scheme in synthesis. We'll take a look at the following problem. Propose a synthesis of this desired product from these starting materials. I highly suggest you employ retrosynthetic analysis and you pause this video, giving yourself about 5 minutes to at least propose the synthetic intermediates. We identify a tertiary alcohol and ketone functional groups in the desired product. We think that these 6 carbons map onto these 6 carbons. And if we're thinking about the tertiary alcohol, it would make sense if this bond was made. The carbon that is the tertiary alcohol carbon, that could have been a carbonyl carbon. And the carbon on the other side of the bond that's made, that would have been a nucleophile. That atom is carbon, so that nucleophilic source of carbon is maybe some sort of Grignard reagent. Okay, now we can imagine those 2 atoms making a bond, and that should yield this product after workup, right? Easy peasy. Well, what stands out to us here? Yikes! This Grignard reagent we proposed contains an electrophile that is reactive with Grignards and a Grignard reagent in the same exact molecule. Those 2 functional groups are not going to be compatible. All right, does that mean we're out of luck? Can't do this? No. We're going to protect the ketone. We'll need to protect this. If you'd like to pause and revise your plan, go ahead and do that now. We'll need to protect the carbonyl, and we'll need to convert the alcohol part into a Grignard reagent. Let's protect the carbonyl first. I will choose to make the dimethyl acetal using methanol and catalytic strong acid. However, as we discussed on the previous page, you could choose many different alcohols resulting in many different acetals. But the point is, we've protected the ketone as an acetal. From this part, we're ready to convert the alcohol into a Grignard, right? This carbon here, right here, needs to become this carbon, looking down in there, key Grignard. It's going to be the nucleophile, adding to electrophilic carbonyl compound. Okay, we make Grignard reagents from alkyl bromide. So the first thing that we should do here is convert the alcohol into an alkyl bromide using phosphorus tribromide. Now we'll treat with magnesium metal in the presence of an anhydrous ether solvent to generate the Grignard reagent. Although we initially proposed this Grignard reagent, which had 2 incompatible functional groups, we have since protected the carbonyl as an acetal. And now the Grignard we have proposed in our synthesis, this one right here, is perfectly fine. There are no incompatible functional groups. To this Grignard reagent, we will add the electrophile that we have already identified, acetone, followed by an acidic aqueous workup to protonate the tertiary alcohol that provides this proton here. Okay, we did it. So our answer is what's written in blue. Our pink is our invaluable retrosynthetic analysis. Now that we've practiced with this problem, let's try again. I would like for you to use what you learned on the previous problem to propose a synthesis of this desired product from this starting material. Do your best. Give yourself 5 minutes. We notice the tertiary alcohol in the product. We're pretty sure this came directly from this ketone to which a 1-carbon nucleophile was added. However, just looking at this combination of reactants should make us feel a bit uncomfortable. And that's because the starting material contains both a ketone and an aldehyde. It looks like the ketone reacts, but the aldehyde should be preserved in the product. However, we know aldehydes are more reactive than ketones. And Grignard reagents are so reactive that if I mix up these 2 molecules, that Grignard reagent is going to react with both functionalities. We're really not going to be able to prevent it. And after workup, we will observe incorporation of 2 methyl groups. All right, that's not what we want. So there's some functional group incompatibility here. So what should we do? Yes, we should protect the aldehyde. Now, we can protect the aldehyde precisely because it is more reactive than ketones. So this is a blessing and a curse. And because aldehydes are more reactive than ketones, this will actually work. If we treat this starting material with a catalytic acid and an alcohol, and we're careful, meaning we monitor the reaction, we will be able to stop it after just the aldehyde has reacted to form the acetal. Aldehydes are reactive enough than ketones that in the presence of a weak nucleophile like an alcohol, we can selectively react with the aldehyde over the ketone. I can assure you of that. I have done it myself in lab before. But again, this is not with any nucleophile. It's really with weak nucleophiles. If we hit this with a Grignard, both functional groups would certainly react. But as we learned in the previous unit, because aldehydes are more reactive than ketones, they can be selectively protected as acetals. From this acetal intermediate, we can add that one carbon nucleophile to generate, after workup, the tertiary alcohol that is found in the product. The synthetic intermediate can be subjected to hydrolysis conditions to unmask, to deprotect the acetal and reveal the aldehyde. The diol is released from the acetal, but this is not the organic product that we care about, so we sometimes don't even mention it. So this synthesis involves the protection of the more reactive aldehyde, the stuff, in this case it's a nucleophile addition, to the ketone, which is the only electrophile left. And then after we do stuff, we deprotect to re-reveal that aldehyde functional group. Fun, right? I had a lot of fun. Let's try again. So let's propose a synthesis of this molecule from the given starting material. And our theme right now is selective reactivity. So we just exploited the relative reactivity of aldehydes versus ketones to do a selective protection of the aldehyde. And now we're going to continue talking about selective reactivity in the context of this synthesis reaction. Give it a shot. Set a timer, 5 minutes. For this problem, we identify this key bond that was made from the starting material to the product. We notice that one of the atoms making the bond is an alpha carbon. And so that suggests that this species acted as a nucleophile from that alpha carbon, which means that the other carbon involved in that key bond forming step must have been electrophilic. So there are these 3 carbons, and then to the carbon that makes a bond to the alpha carbon must have been bonded some leaving group. For 2 reasons. It's gone now, but also that electronegative leaving group makes that carbon electrophilic. It makes it have a partial positive charge. When electrophilic sources of carbon are needed, we have some possibilities. There are carbonyl compounds, epoxides, and alkyl halides or tosylates. In the case of carbonyl compounds and epoxides, the oxygen will remain in the product, and we don't see any heteroatoms left on that carbon group that was added. So we're pretty sure it involved an alkyl halide because in alkyl halides or tosylates, the leaving group just leaves, then it's gone. You should be able to draw out electrophilic and nucleophilic sources of carbon. I believe we've identified our key carbon-carbon bond forming step. I will need to treat the ketone with some base to generate quantitatively this enolate. Quantitatively means 100%. The equilibrium of this acid-base reaction needs to favor the products. Because in the second step, when we add the electrophile, which is an alkyl bromide, this is called an alpha alkylation, and it requires generation of the enolate first. So whatever this base is, it needs to 100% make the enolate. Now we know a base that does that. That base is lithium diisopropyl amide, otherwise known as LDA. Lithium diisopropyl amide. Usually, lithium diisopropyl amide would deprotonate the less substituted alpha carbon. In this case, we'll call that alpha prime. So typically, lithium diisopropylamide deprotonates the less substituted alpha carbon rather than what is desired here. What is desired is deprotonation at the more substituted alpha carbon, the tertiary alpha carbon, to generate this enolate. Just comparing the two enolates, we see that this one, the desired one, looks like a tetrasubstituted alkene. Whereas this one resulting from deprotonation to alpha prime looks like a disubstituted alkene. Thus, this enolate is more substituted and represents the more stable alkene. It's referred to as the thermodynamic enolate. It is more stable because it is more substituted. Whereas the enolate from deprotonating at alpha prime is referred to as the kinetic enolate. With a bulky base like LDA, it is simply just lower energy for that base to deprotonate at alpha prime where there's less electron repulsion from other substituents on that carbon. So this enolate is desired, the thermodynamic enolate is desired, but usually LDA makes the kinetic enolate. So what are we to do? Well, you're not going to give up. So what are we to do? We have learned in the past that treatment with the bulky, strong base LDA quantitatively generates the kinetic enolate when the two alpha carbons have different substitution. Whereas protonation with a weaker base, such as an alkoxide base, favors formation of the thermodynamic enolate, but the equilibrium of this reaction certainly favors the starting ketone and alkoxide. So the enolate, thermodynamic enolate, is made in small concentrations. For alpha alkylations, like proposed in this synthesis, it's necessary to generate 100% of the enolate before treating with the electrophile. So although small concentrations of enolate were okay in, say, an aldol concentration, they're not in alpha alkylation. Our chemists have come up with a way to deal with this, to use LDA to quantitatively generate both the kinetic and the thermodynamic enolate. Let's start down at the bottom. If we ensure or we use just a bit more than one equivalent of LDA, just as expected, the kinetic enolate is formed. Bulky LDA deprotonates at the less sterically hindered of the two alpha carbons. However, if one treats with just less than one equivalent of LDA, just less, first, certainly the kinetic enolate is formed. Right, LDA is bulky, it deprotonates at the less substituted of the two alpha carbons. However, because we use less than one equivalent, there is some starting ketone left. So let's say we have 95% of the enolate and 5% of the starting ketone. That starting ketone still has an acidic proton. So basically what happens is this ketone protonates the enolate and eventually equilibrium is reached by a series of proton transfer reactions between the enolate and the ketone forms of the same molecule so that the thermodynamic enolate is formed. All right, the lower energy thermodynamic enolate can be obtained by treating with just less than one equivalent of LDA. Let's summarize how we can use LDA to generate the thermodynamic or kinetic enolate and then use it in further reactions. So again, with just less than one equivalent of LDA, although first the kinetic enolate is formed in solution, equilibrium can be reached to form the more substituted thermodynamic enolate, where there's a tetrasubstituted double bond versus a disubstituted double bond, and the kinetic enolate, which is obtained by ensuring that you've used just more than an equivalent of LDA so that the less substituted alpha carbon is completely deprotonated at the less substituted position, generating the kinetic higher energy enolate. Either the thermodynamic enolate or the kinetic enolate, depending on the product desired, can be alkylated to generate a substituted ketone, made a carbon-carbon bond. How will you know which conditions to use in a synthesis problem? Well, it depends on which alpha carbon is reacting. For the more substituted alpha carbon undergoing a substitution overall, right? Substituting hydrogen for the alkyl group, that will proceed by the thermodynamic analyte, which if it needs to be generated quantitatively, can be done so by using less than an equivalent of LDA. However, if the less substituted alpha carbon undergoes reaction, then we know the kinetic analyte is necessary, using just more than one equivalent of LDA. Let's apply what we've learned to the synthesis problem at hand. Take a moment now and write out the synthetic scheme for the transformation of this ketone to this product. As we discussed, the key carbon-carbon bond forming step in this reaction is an alpha alkylation. Alpha alkylation requires formation of the analyte. The thermodynamic analyte is desired rather than the analyte that would have resulted from deprotonating the less sterically hindered alpha carbon. This would be the kinetic analyte. This would be the thermodynamic analyte. Both analytes are possible because both alpha carbons are analyzable. They contain alpha hydrogens. Using slightly less than an equivalent of LDA at -78 degrees generates the desired analyte, followed by treatment with the electrophilic allyl bromide leads to the desired product. What does it mean for a reaction to be selective? Yes, selective reactions occur when there are more than one possible reactive sites in a molecule, such as when there are two alpha analyzable protons in a ketone such as this one. A selective reaction favors one of those reactive sites. For example, treatment with a base would favor reaction just at the more substituted alpha carbon. So this would be true for alkoxide bases, or if you use less than one equivalent of LDA, equilibrium will occur and this product will be formed. Let's list the selective reactions that you know, the reactions where more than one possible reactive site is present, but one of the reactive sites are favored. You know some selective reactions to alpha-beta unsaturated carbonyl compounds. Some reagents favor addition to the beta carbon, whereas other reagents favor addition to the carbonyl carbon. Those reactions that favor one site over the other are examples of selective reactions. We've learned that aldehydes are more reactive than ketones, and so we selectively protected an aldehyde as an acetal instead of the ketone, exploiting the difference in reactivity. We've seen that sodium cyanoborohydride only reduces iminium ions. Even in the presence of a ketone, only the iminium will be reduced. We will soon see that certain functional groups will react selectively with sodium borohydride as well as we proceed into the next part of the course. Well, there are probably some other selective reactions that you know, so list them, and be thinking about them when you're solving synthesis problems. Speaking of solving synthesis problems, let's try one more problem before we end this video. So propose a synthesis of this desired product from the starting material. As with the other problems in this lecture, pause and give yourself 5 minutes. At least practice retrosynthetic analysis to draw out the identities of the intermediates from which this molecule might be made. We notice an alpha-beta unsaturated ketone in the desired product. We can map on the carbons noted in pink and feel pretty confident that these are those same carbons in the product. We know that alpha-beta unsaturated ketones, such as the one found in the desired product, are made via aldol reactions, where the alpha carbon was an enolate and the beta carbon was a carbonyl compound. We imagine breaking this alpha-beta bond and replacing it with the functional groups from which they were made. Okay, so going in the forward direction, we'd be proposing an aldol reaction, which can be affected by aqueous sodium hydroxide or an alkoxide. I'll propose an alkoxide base to affect this aldol reaction, but you could perform this reaction under acidic conditions or with sodium hydroxide as well. Sodium methoxide would generate an enolate at the alpha carbon, which would attack the aldehyde to generate a 1, 2, 3, 4, 5, 6-membered ring as seen. After elimination of water, the double bond would be generated. And taking a look at the starting material, we can map on those carbons to this key intermediate, and we can see that a bond needs to be made right here. All right, that bond is made to an atom that is beta. All right, so lots of alphas and betas in this analysis because there are multiple different carbonyl compounds. But we see this key bond that needs to be made is to a carbon that is beta to a carbonyl. So that tells me that could be made via a conjugate addition. The conjugate addition to this beta carbon happens from the other alpha carbon of the ketone. So it happens from the more substituted alpha carbon of the ketone. This ketone, of course, is the one that is given to us as starting material. An enolate plus an alpha beta unsaturated ketone. So the enolate as a nucleophile for addition to an alpha beta unsaturated ketone, that's a Michael reaction. And we're proposing a Michael reaction followed by a aldol reaction. These transformations are actually facilitated by the same reagents. So Michael reaction is just the name of enolate plus an alpha beta unsaturated ketone. So these two reactions are actually affected by the same conditions, and you might remember that this sequence, Michael reaction followed by an intramolecular aldol reaction, is known as a Robinson annulation. Oftentimes those two reactions happen all in the same pot. So we could write it out step by step like we did here, or we could just propose the Robinson annulation in a single step. So we have the alpha beta unsaturated aldehyde and an alkoxide base to generate all those enolates. The conjugate acid of the base is given as the solvent and the proton source. And this would work because alkoxide bases will form the thermodynamic enolate, even though the equilibrium constant is less than 1. Once the thermodynamic enolate is formed, it will add to the alpha beta unsaturated ketone in a series of steps. So nucleophilic addition, proton transfer, generate this intermediate, which will continue reacting, forming the enolate at the alpha carbon and undergoing aldol condensation to generate the desired product. If you need to write out that mechanism, you certainly can. In synthesis problems, though, it is not required, though I needed to be thinking about it to propose the synthetic intermediates. Okay, if you're panicking, you need to stop panicking. Make your reaction charts. Once you have your reaction charts, your list of reactions, you have reagents, conditions, and products. Be sure that you're labeling functional groups, so that's how you will recognize the reactions. Once you have the list reaction chart, you should make new reaction charts organized by functional group. These are really helpful. I've mentioned them several times in these videos. So think about all the different ways that you can make alkenes so that when you encounter an alkene, you say, oh, that could come from A plus B in acidic. That could come from these two in a dehydration. So think about all the different ways that you can make the most commonly encountered functional groups. And then the most important step really is that you do a lot of practice. After this video, we're able to propose synthetic sequences featuring nucleophilic addition reactions to polar pi bonds as key bond-forming steps. We've identified synthetic traps such as functional group incompatibilities. We've looked a lot at carbanions plus proton sources, be that water or alcohol or even carboxylic acids. Or We also looked at carbanions with carbonyl functional groups that we did not want to react. We learned how to apply protecting groups for both alcohols and ketones and aldehydes so that we could mask those groups, do stuff to the rest of the molecule, and then remove the masks, unhide the alcohols and ketones in the final products. All right, it's time to practice. There are lots of practice problems. Before you do that, summarize and let me know if you have any questions.